we are given this situation here to find the critical points of the function f of x and y, given the constraint g of x and y. Alright, so here our function is x squared plus y, and our constraint is x squared plus y squared equal 4. You practice to rewrite the constraint so that all the x's, y's, and the numbers are on the left and then equal 0 on the right, because we're going to differentiate it at some point. Now, remember this particular equation here that applies to it. The gradient vector of the function is equal to a scalar multiple, which we call the Lagrange multiplier, represented by the Greek letter lambda. That is equal, that multiplies the gradient of the constraint. Alright? And you remember the argument behind it is that you have this three-dimensional surface, right? And it is in our graph of x, y, z. And you could find points anywhere on it you want, but then you have a certain constraint, right? You could be constrained by the budget, could be the customer demand. There are only so many people to sell to and no more. It could be environmental or other laws. It could be technical constraint, that's temperature or the strength of the material. It could be factory space, could be time constraint, all sorts of constraints you might meet upon. So if you operate within this region, you cannot pass below this line, the constraint line. It's a boundary. It limits you. Let me redraw the constraint. Could be because of the shape of the surface. It could be this. And you might have a minimum point right down here. Right? And you have a tangent to that minimum point. But you can also have a tangent right here. And if you slide this tangent over to meet this other tangent, you have a 90 degree between them, right? And this tangent, let me redraw the tangent in a different color. Let me draw it black. This tangent, you can represent it as a vector representing the gradient vector of the function, and then this other one, this other tangent, is the gradient vector of the constraint. And they won't generally be the same length. So you have to multiply the constraint. Well, the constraint could be longer or shorter. You have to multiply the constraint by a number to get it to be equal to, or the constraint, or the constraint vector by a number to get it to be equal to the, in magnitude, to the function vector. So that number would be the Lagrange multiplier, which we have here, right? So here we're going to find out what is the vector, the function vector. So let's go. The function vector, gradient vector, is equal to delta f by delta x in the I direction plus delta f by delta y in the j direction. If you look elsewhere, you might see it written in another way. It could be delta f by delta x comma, delta f by delta y in angled bracket. But even the derivative could also be written as f sub x in the I direction plus f sub y in the j direction. Or it could be in angle bracket f sub x comma f sub y, right? Could be that. But I like writing it using the delta and the I and j. Alright, so what is delta f by delta x? From looking at it, if you differentiate this with respect to x, you get 2x, and that's in the I direction plus, and if you differentiate this now, the f of xy with respect to y, you get 1. So it's 1j. Or you could just write j. You don't really need the 1 anymore. You see that? And then, what is the delta g? The gradient vector of the constraint g. In this case, delta g by delta x in the I direction plus delta g by delta y in the j direction will give us 2x in the I direction plus 2y in the j direction when you differentiate this, right? You see that? Alright, so here now, what happens? If you look at this formula, very important formula, in fact, let me underline it, right? Very important formula, right? When you look at this, you can rewrite it in that form. You have delta f, which is 2xi plus j is equal to, then you have the Lagrange multiplier times 2xi plus 2yj. Good. Well, then we could just rewrite it and multiply by the Lagrange multiplier. 2xi plus j is equal to, write it as 2x lambda I plus 2y lambda j. Alright? So that's what you have. After that now, okay, you have there, being disturbed by mosquitoes. Alright, yeah, back to what we're doing. So, all we're going to do is equate the coefficients of I and j. So, this 2x would be equal to the 2x lambda, right? So, we have 2x is equal to 2x lambda, because whatever multiplies I is equal to, in the gradient vector of the function, is equal to whatever multiplies I in the gradient vector of the constraint. Same thing applies to j, but in this case it is 1j equal 2y lambda j. So you could say 1 is equal to 2y lambda. Remember, you don't bother to write the j and the I and j. You don't need that because they would cancel out anyway. Because if you write them, you'd have to have 2xi equal to x lambda I, and the I would cancel the I. Alright? You can write it down if you want, but you'd have to cancel it anyway. Alright, so this is equal to this. Now we have these equations. It's a pair of simultaneous equation. guess what now? You see that pair of simultaneous equation? They are giving you the gradient of these two vectors. But where these two vectors are, the vectors, you know, they could have been here, here, they could have been here, here, wherever they want to be. But you want the vectors to be on the constraint, right? You want it to be on the constraint. So you want to find where both vectors meet as well as where the constraint is. Both vectors should meet on the constraint. So you're going to have a third equation, which is the constraint. X squared plus y squared equals 4. So here you have x squared plus y squared equals 4. So you have three equations here. All you do now is just work them out. Solve them to find x and y. So you know the location of the constraint. You might also find lambda. It's not really necessary, but if you're asked to do it, then you just do that. Alright? So, since we have three equations to solve, we have simultaneous equations. Call this equation 1, this equation 2, this equation 3. Alright, so you see how you're going to solve it now. Let us see what's going to happen. Look at equation 1. If we look at equation 1, 2x is equal to 2x lambda. If we divide by 2x, cancel, then all you have to say is that 1 is equal to lambda. So lambda is 1. Alright, so you know your lambda now. And in fact, it shows that both of the vectors, the gradient vector for the function and the gradient vector of the constraint, they have equal magnitudes as well. So they are equal. Alright. So the magnitudes are equal. It's positive 1. Since lambda is 1, we can say 2x is equal to 2x. But that won't help us too much. Let's look at equation 2. Lambda is 1, so we can say 1 is equal to 2y. So if we divide by 2, we get y is equal to half. Alright, we know the y now. So now we know that y is equal to a half. We can substitute that in equation 3. Substitute in equation 3, alright? So equation 3 says x squared plus y squared. You can just write half squared equals 4. Good. Alright, so here, half squared. This would be x squared plus a quarter is equal to 4. Alright? If we should subtract 4 from both sides, we'd have x squared is equal to 4, subtract quarter from both sides. We'd have x squared is equal to 4 minus a quarter, which is what? 4 minus a quarter. 4 over 1 minus 1 over 4. We get common denominator. So multiply 1 by 4. If we multiply under here by 4, we get 4. If we multiply up top by 4, we get 16 up top. Alright. So in this case, 16 quarters minus 1 quarter gives us 15 quarters. Good. That's x squared. So x is equal to the square root of 15 over 4. But don't forget the positive and negative. Alright? We could write this as positive and negative square root of 15 over square root of 4, which is square root of 15 over 2. You could have it like that, alright? Now, here, that's the square root of 15 over 2. And we have, we're going to deal with this now. So, we have x is square root of 15 over 2. Now, we already have one value for y. But if we try playing around with it a bit for y into, let's see if we can find any other value for y here. When x is equal to square root of 15 over 2 in equation 3, what is y? Well, we have x squared. So if x squared is 15 over 4, we have 15 over 4 plus y squared equals, what is it again? 4. 4. So x squared is 15 over 4, we put it here. So y squared would be 4 minus 15 over 4, which would be 16 quarters minus 15 quarters, giving us 1 quarter. So y squared is that. So y would be positive and negative square root of a quarter, which is a half. Alright. It takes us back to the half. Now, here, let's find the coordinates then. When x is equal to this, when x is equal to positive square root of 15 over 2, we're going to find out what happened with y. And when x is equal to negative square root of 15 over 2, what happened to y? Let's see. When x is, well, it would make a difference, because when we put in x squared, we would get 15 over 4 just the same, whether it's positive or negative. Right? So y would remain half. Right? Is y ever negative half? We get y is half already. So x squared plus y squared equals 4. When x is 15 over square root of 15 over 4, then y would be positive or negative half. But we already confirmed that y gives us half, so it doesn't seem as if it's ever negative half. So in this case, our coordinates is 15 over, let me see, what is it, 15 over 2, square root of 15 over 2, comma, half, and negative 15 over 2, comma, half. Those seem to be our coordinates, right? So those are the coordinates of the maximum and minimum point. Now, those are the location of the critical point. We were not asked to find out what is the nature of each. Alright? But let's finish off here, and then in our next video we'll summarize it and then find out what the nature of each of it is. So I'll see you then.